down to the last 2 weeks. This week you will get one more homework assignment on paper and one more computer assignment. That will be the last one. So you will not get one next week because I like to wrap everything up before final. I have no idea what your grade will be until I get the final exam grades, the final exam numbers, and then I'll put together the grades. Most of you are doing well. I'm paying attention. I see who comes to class on a regular basis, so I wouldn't worry too much. When I was just talking to a student in my office. He was all worried because he said, I'm not doing that well, different class. The professor says, don't worry, you're doing fine. When we say don't worry, you're doing fine, we know you're not failing, okay? Unless you surprise us. In fact, you're probably doing okay. But we can't tell you, we can't say, oh yes, you're getting an A, because then if I don't give you an A, you'll be upset because you said, I'm getting an A, right? So I can't tell you how you're going to do. I can just say that most of the people in the course are doing reasonably well to very well. Some of you could do better, but just keep up the good work, try to do well in the final. It'll all come out okay. Right? I can't promise you A's, but very few of you are in danger of getting below C. A few. Some of you are really challenging that. And for many of you, C is good enough. You'll take the C now and you'll leave. In fact, if I offered you a C and no final exam, you would say yes. Okay? Which I understand. Some of you want the A, which is also fine. You should try to do the best you can. But don't stress too much about this course. I will make practice problems for the final. I will do a practice final exam. Even though I didn't do it for the midterms, I will make you guys a sample final exam. The final is 2 weeks from Wednesday. I think I may have to, oh, and there goes the microphone. Battery dead. Do we have a replacement battery? No. The final exams talk scared off the microphone. Anyway, what was I saying? Practice final exam. Oh, room. I don't know yet what the room the final will be in. I have it on my computer. I'll post it this week on Blackboard. It's not the same room as the midterms. I think it's somewhere in that. I will find out, okay? So there you go. Anybody have any questions before we get going? All right. So we're now going to do one of the more annoying topics in integration. So you learned how to take derivatives, and then you did, the product rule, the quotient rule, and the chain rule. Now we're going to do integration. And there's lots of technique of integration. There's all sorts of integrals that are not obvious what the original derivative was. So remember I told you, it's very easy to go, relatively easy to go from derivative to integral. It's very hard to go backwards because when you do the derivative, you can take something simple and you end up with this mess. It's very hard to look at something in the integral and figure out from that mess what the original function was. It's working backwards is hard. The good news is in this course, we really don't cover any of that stuff. We leave almost all of it out because, frankly, that's an entire semester's worth of stuff to cover. And it's really not relevant to what you're doing. But you should learn how to do what's called substitution, which is really working the chain rule backwards. So let's think again about what our three main types of integrals are. You'll have an integral form u to n, and the antiderivative, the integral of that. That's when you have something to a power. So that's form number one. I'm using u for a specific reason. You can have an exponential, where you have e to the u times a constant. It's just e to the u times a constant again, divided by whatever the constant was. The third main type we get, for example, 1 over. So what we're going to do with substitution is you're going to take an integral that doesn't immediately look like one of these and play with it to turn it into something that looks like one of these three. So once you can do that, then it's very easy to integrate. So you use this technique called substitution, where you take the integral and you substitute some stuff into the integrand to make it easier to work with. Once it's one of these three forms, you can integrate it and then you just substitute back. For example, suppose you have something that looks like that. Well, this is really 5x minus 3 to 1/2. So it's something to the half. So we know how that's the first type, right? It's a function to a power. So how are we going to get this to look like u to the half? Well, what you do is you look at this and say, let's let u equal 5x minus 3. So you can use any letter you want, just u seems to be the one that's additional to u. So if u is 5x minus 3, then the derivative of u is 5. Or if you cross multiply this, you could say du is 5 dx. That's u. It's sort of traditional to break the derivative up like that. So now you can look in here in the integral, and you can say, well, I could substitute u for 5x minus 3, and I get u to the half. But I have to replace dx, because if this is in terms of u, then I have to have a du. I can't have a dx. So du would be 5 dx, but I only have 1 dx, so all I do is I make that 1/5 of du, so divide both sides by 5. And now I can come to this integral, and I can substitute. I can say, well, this 5x minus 3 is now going to be u to the half, and dx is going to be 1/5 du. Or if I move the 5th to the outside. So what I've done is I've just sort of rewritten this as an integral of the form type 1. I made it into a power. And really just by playing around with constants. It's not really that fancy what I'm doing. But let's do a few of these so you get the hang of it. Now if you integrate this, you get 1/5 of u to the 3/2 over 3/2. You okay there? Which is 2/15 u to the 3/2. And then if you substitute back, remember u is 5x minus 3, you get 2/15 5x minus 3 over 3/2 plus a constant. So if you look at this, the square root, it's not obvious that you get that 2/15 term. So what the u substitution does is it helps you figure out what that constant is. It really works the chain rule backwards. Since we need this, if you take the derivative, you get the 3/2, that's going to come in front. 5x minus 3 to 1/2 times the 5. So that 2/15 helps you get the constant right. Yes. Question? Let's do a few of these. Make sure we get the hang of it. So very similar to the other one. So we've got 8x minus 7 to the 10th. Of course, you can multiply that out. So the derivative of that is not very hard. So if you want to do the integral, well, the problem is the 8x minus 7. You can't just say it's 8x minus 7 to the 11th over 11, because if you take the derivative of that, you won't get this. So you have to play with it a little bit. Okay? You can't just make this to the 11th over 11, because as I said, if you do that, and you took the derivative, you won't get back here. You'll be off. So the u substitution helps you figure out how to do that, how to get the constant right. So you let u equal 8x minus 7, then du dx 8. Cross multiply. And now you look at the integral. You say, okay, well, I can substitute the 8x minus 7, and I can substitute for the dx, but just divide by 8. Now, I can take this integral and make this u to the 10, because this is u, and this is 1/8 du over 1/8 u to the 10 du. so u to the 10th becomes u to the 11th over 11, or u to the 11th over 88. And then you substitute back. Okay? All right. Suppose I had that. So one clue is this is a higher power than x, 6x squared minus 4. So if I make this u, the derivative would be 12x. And I just have to play with it to make it look like x. If I made this u, the derivative of that is just 1, I wouldn't have anything to substitute here. So I'm going to let u equals 6x squared minus 4. Then derivative of u is 12x, or if you cross multiply, du is 12x dx. I'm going to start skipping that du dx step. So I look at the integral. Yes?
Is it the du ultimately is the dx?
Yes, all I'm doing is I'm putting this over here. Because I want to substitute, I want to isolate du. So in the integral, remember we had this d term. You always wondered why that was there. Now you know. Okay, it comes out of the derivative. So we have to replace everything in here that's in terms of x. Replace it with something in terms of u. So I look at the integral and I say, well, I can replace this 6x squared minus 4. And I've got x dx, that's x dx. I just have to divide by 12. And now I can substitute. I can say this becomes u to the half. And x dx becomes 1/12 du, or if I move the constant outside, I get 1/12 of u to 1/2 du. I get 1/12. Here I had du is 12x. So if we divide both sides by 12, that becomes 1/12 du. Okay? And once you have a constant inside the integral, it's always a good idea to move it out so it doesn't clutter up the integral. You just don't worry about it too much. You just figure out all the constants and you're done. So this is 1/12. Integral of u to the 1/2 is u to the 3/2 over 3/2, which becomes 1/18 u to the 3/2. And then substitute back. 6x squared minus 4 to the 3/2 plus constant. Which, as I said, is not obvious when you start with something like that. They can get significantly messy, but we won't get to too difficult ones. So have you guys practice one? By the way, you could just multiply this whole thing out, and then it would just be a polynomial you could integrate. It's hard. So I would let u be 5x cubed plus 11. Not to the 4th, just 5x cubed plus 11. Because if you put the integral of u to the 4th, then you can work from there. Okay. We got it? Yeah? Some of you still look like you're struggling a little bit. Okay. Okay. So one of the clues is when you have two terms in the integrand. One of them is an x to a power, the other one is the x to the lower power. The x term to the higher power will be u. So let u equal 5x cubed plus 11. And then you take the derivative. So du will be 15x squared dx. This is really du dx, but You move the dx to the other side. Then I look at the integral and I say, can I substitute? Well, this can be u, and x squared dx, well here I have x squared dx, so just have to divide by 15, 1/15 du is x squared dx. So I can take this integral and rewrite it as u to the fourth times 1/15 du, or 1/15 of u to the fourth du. Yeah, it can get more complicated, but so far.
Okay.
These are all the very simple ones so far. Generally, we're not going to give you the hard ones because they involve trig and combinations of messy functions. But there's some tricky ones. I just don't know if I'm going to bother with those or not. I know you guys are voting don't bother, but I'm just going to sort of look and see, bring the book with me, whether the book bothers or not. I don't think it does. So the idea of the course is to teach you some basic tools, not to turn you into integrating machines. All right, so integral of u to the fourth is u to the fifth over 5. Well, you don't really write the plus c till the end. You really want to be correct. So that's u to the fifth over 75. And then you substitute back. So that's 5x cubed plus 11, 5 over 75 plus a constant. As I said, when you look at the function initially, you don't always say to yourself, oh, sure, that's going to be over 75. You have to sort of get that part right. Why is that true? Let's take a derivative of this, just to check. Well, the derivative would be 5 times 5x cubed plus 11 to the 4 times 15x squared. Okay? Because the derivative of something to the fifth is 5 times something to the fourth times the derivative of the inside, and the over 75 just stays there because it's just a constant. And then if you simplify, well, 5 times 15 is 75, so they cancel, and you get the x squared and 5x cubed plus 11 to the fourth, which is what we want to get. Okay? So as I said, so this helps you work the chain rule backwards. Okay? Let's see how that one goes. All right. Let's do this one. So if you let u equal x squared plus 4x plus 1, this would become u to the 1/2, which is good, because that's what we want. So we have to turn x plus 2 dx into du. So let's take a derivative. And you get 2x plus 4 dx, because the derivative of x squared plus 4x is 2x plus 4. And you say, well, it's almost x plus 2. If I just divide this by 2, so I have 1/2 du, that equals x plus 2. So now I can go to the integral, and I can say this becomes the square root of u, or u to the 1/2. This becomes 1/2 du. Or it's 1/2 integral of u to the 1/2 du. You'll see what I did? Okay? So again, so you look at the integrand and you say, I've got to turn one thing into u to a power, and then everything else has to become du. So if I let u equal x squared plus 4x plus 1, and the derivative of that is 2x plus 4. I don't have 2x plus 4, but I have x plus 2, which is just half of 2x plus 4. You just divide this by 2. Now the half du is x plus 2 dx. Now I can go here, and I can substitute everything. This becomes u to the half. This becomes 1/2 du. All right, what's the integral of u to the 1/2? It's u to the 3/2 over 3/2, where this is 1/3 into 3/2. And now you substitute back. So I said, not obvious how you go backwards. You can imagine, you can get some very messy integrals in here that turn into something very simple, or something very simple in here that turns into something quite messy. So, we don't do trigonometry, but, the integral of secant cubed, you get this long, complicated thing, which you take the derivative of, it just becomes secant cubed. But it's a long mess, so it's not always obvious how it goes the other way. I'll do another one. Suppose we're going to do x e to the x squared. We can take the derivative of that, that's the product rule. We want to do the integral. So remember what the integral of e is. Right? The integral of e is just e, really. Right? E to the u is just e to the u. So we just want to kind of turn this into an e to the u. So we have to get rid of that x somehow. So if we let u equal x squared, derivative of that is 2x dx. Notice we have x dx. We almost have 2x dx. Right? We have this, x dx, and that, x dx. So if I move this constant, I can now rewrite the integral as this is e to the u. And the x dx is 1/2 du. I just put the half in the outside right away. You all see what I did? So again, you let u equal x squared, not e to the x squared, just x squared. And the derivative of u is 2x dx. I only need to substitute for x dx. So if I pull this 2 out, I get 1/2 of du is x dx. Now, integral of e to the u is just e to the u. And now you substitute back. So it's 1/2 e to the x squared plus a constant. Okay, I'll give you an entertaining one. Don't be scared off. Remember, we want to make this into e to the u. So if you let u be the square root of x. Remember what the derivative of the square root of x is? 1/2 root x. Which is almost what we have. We just have 1 /the square root of x. We don't have the 2 in there. So if I multiply this by 2, I get 2 du. 1/the square root of x dx.
Why is it 2?
Because I want to have this. I want to have dx over the square root of x, which is this. I just have to get the 2 on the other side. So now this integral becomes 2 integral of e to the u du. Because 2 du is dx over the square root of x. That's 2e to the u plus a constant. Whoops. Just 2e to the u, sorry. Which is 2e to the square of x plus a constant. All right, you ready? So, let's let u equal 4 minus 3x squared. Du minus 6x dx. This is derivative of 4 minus 3x squared. So if I divide by negative 6, now I have to get to the lower limit. So I can substitute for 4 minus 3x squared. I can put it in u, and I can put in negative 6 du for the x dx. And I get e to the u, du. So that's the key, is that the chain rule helps you get rid of all this other stuff and turn it into a nice simple integral. So again, the x dx is here, and that's negative 6 du. Now integrate, you get that's equal to negative 1/6 du. And then substitute back. 4 minus 3x squared plus a constant. All right. This one. All right. So what do you think I'm going to let u be in this one? U is x. If u is x, then I don't get anywhere. I can't do that. Any other ideas? I'm going to let u be 1 plus e to the x. Well, if u is 1 plus e to the x, du would be e to the x, dx, which is exactly what I need to substitute for. This is a general idea. Like if you see a radical, let u be the thing that's under the radical. So this becomes the square of u. This becomes du. Integrate this, you get u to the 3/2 over 3/2, which is 2/3 u to the 3/2. And substitute back. How do we feel about these so far? They're a little trickier. As I said, there's lots of different types of integrals and all sorts of tricks to work them backward. When calculus was being developed in the 17 and 1800s, obviously some people would come up with one and say, I have no idea how to do this. And then a bunch of people would throw their brains at it until somebody came up with a clever idea and said, oh, here you go. Then they generalized and said, always use this technique, and there you go, we conquered another type of integral. Some of these integrals are really tricky, how you integrate them. Fortunately, you guys won't have to deal with that. And these days, computers can do all the integration you want. They can do numerical integration, which is the rectangle stuff, sort of. And then they can do actual symbolic manipulation. We do a lot more of this on Wednesday, so have a nice day.